right. Good day, mathematicians. Congrats, we're on our third unit of Math 8. This is awesome. This unit is called Growing, and I'm going to abbreviate it GGG, okay? This unit is all about exponents and this thing called exponential growth, or exponential decay. We've talked a ton about linear relationships, and I think it's about time that we start to look at things that aren't linear, okay? So hopefully this sates some of you. All right, the first thing I want you guys to take a look at is the table of contents. You'll notice that lesson 4.1 and 4.2 are on page 39. That is incorrect. Only 4.1 is on 39. So if you guys can go ahead and change your page numbers so that way they are accurate, and that way you don't get lost. Okay. So make sure those are changed. All right. But with today's lessons, we're going to cover two lessons. So that's 1.1 and 1.2. Introducing you guys to this idea of what we call exponential growth. We're going to be taking a look at a problem, specifically making voting ballots, right? The California primary is coming up, so might as well talk about voting. All right, so your focus question for today, or for this lesson, I should say, what are the variables in this situation and how are they related? So we're talking about our independent variable, our dependent variable. How do they affect one another? Okay. Now let's read for a little bit of context. So Chen is the secretary of the Student Government Association. He is making ballots for a meeting. Chen starts by cutting a sheet of paper in half. Then he stacks the two pieces and cuts them in half again. With 4 pieces now, he stacks them and cuts them in half. By repeating this process, he makes smaller and smaller paper ballots. So what we're going to do is we're going to make a table to show the number of ballots after each of the first 5 cuts. Okay, so if you take a look, we have a column for the number of cuts. We have the number of ballots in what we call standard form. We have expanded form, and then lastly exponential form. Okay, so what we're going to write in expanded form for this first column, so when he makes 1 cut, how many ballots are formed? 2 of them, right, because he cut it in half. And for expanded form, it's going to be the same. And then exponential form, well, what is 2 as an exponent? Well, just 2 to the first power. Okay, let's take a look at the next one. Number of cuts is 2. When you cut it again in half, well, how many ballots do you now have? Well, you have 4, right? It looks like it's, I don't know, you guys will notice a pattern pretty soon. And then rewriting this expanded form into exponential form, you would say, hey, that's 2 to the second power. Okay, let's do one more. If I were to cut the 4 ballots in half again, how many ballots would I have? And you might say, I would have 8 ballots. Writing this in expanded form, 2 times 2 times 2, and then in exponential form, we have 2 to the third power. Okay, so I want you to go ahead and pause the video, and I want you to fill in the rest of this table here. The one thing that I want you guys to add in at this very, very bottom row is the variable n. Okay, so go ahead, pause the video, fill in the rest of this table, and we're going to talk about it. All right, I really hope you pause the video, but here we go. So for 4 cuts, we have 16 ballots. Written in expanded form, looks like now we have 4 2's, which is going to help us write our exponent with 2 to the 4th. All right, 5 cuts gives us 32 ballots. 2 times 2 times 2 times 2 times 2, so that is 2 to the 5th power. 6 cuts gives us 64 ballots. 2 times 2 times 2 times 2 times 2 times 2. And I really hope you guys are paying attention to what type of pattern is happening here. What exactly is happening? After you make a cut, what happens to the number of ballots? That should be on our brains right now. 3, 4, 5, 6, 7. So that would be 2 to the 7th power. And then here we have 256. 2 times 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 2. And that is 2 to the 8th power. Are you guys getting tired of the number 2 yet? And then there we have 2 times 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 2. That's 2 to the 9th power. And then when we have 10 cuts, we have 1,024 ballots. And written in expanded form, there we have 2 to the 10th power. Now what I want you to think about, well, what if I changed the number of cuts to n? Okay, what would that look like in exponential form? Well, one thing that I'm noticing is that, hey, the exponent matches the number of times, there's a 2, but hey, it also matches the number of cuts, right? Let's check 2 to the 6th. Hey, look, that matches. So I hope you guys came to the conclusion that when you have n number of cuts, and n can be any number, all you have to do is take 2 and raise it to the nth power, to whatever number you plugged in for n, okay? So let's talk about this pattern. Think about it for a second. Maybe talk to a neighbor. Hey, what pattern did you notice? I'll give you a few seconds. Okay, so after thinking about this pattern, hopefully you came to the conclusion that, well, the ballots, they just double after every cut. Right? We go from 2 to 4 to 8 to 16 to 32 to 64, right? It's doubling every single time that Chen makes a cut. All right, now what we're going to do is we're going to take a look at what this graph looks like. Okay, so if you guys could please label your graph accordingly, just like this. So along the x-axis, we're going to have the number of cuts. Now the number of cuts is our independent variable because the number of ballots depends on it, right? It depends on how many cuts you make. So on the y-axis, we're going to do the number of ballots. All right, and then let's go ahead and go by 2s. We're going to skip every line, so 2, 4, 6, 8, and 10. And then on the left side, on the y-axis, I should say, we're going to go up by 200s because we get quite a bit of ballots as we go along the x-axis. Okay, now go ahead and graph. Go ahead and graph your data, please. So you'll notice that our graph doesn't really like expand or like really increase until we get to like about 7 cuts, right? Because at 7 cuts we're finally past that 100 point, right? And 100 would be right here. And then at 8 we're at 256. 256 is approximately right there. And then at 9 we're at 510, which is approximately right there. And then at 10 cuts, we're at 1,024. We're like off the graph here. So do your best to sketch, please. It's not going to be a straight line, but it is going to be a beautiful curve just like this. And based on what this graph looks like, we can say that this graph shows what we call exponential growth. All right, it says to write an equation that represents the relationship between the number of ballots t and the number of cuts n. Remember, the number of ballots t, this is our dependent variable, and then the number of cuts is our independent variable. So when we write our equation, it has to be in terms of n, right? So we're saying that t, the number of ballots, is equal to what? Well, you'll notice that we already wrote the equation here, right? The number of ballots equals 2 to the power of the number of cuts. So we'll say that the equation is t is equal to 2 to the nth power. Okay, I would like you guys to add this in. This 2 is a very special number, and this is what we call a growth factor. And we'll get into that a little bit later, okay? But because it's a 2, that tells us that it's doubling, that our dependent variable is doubling every single time our x increases, okay? So for the growth pattern, we can say from the graph, this shows, like we said earlier, this shows exponential growth. Did I spell that right? Exponential, yes. Exponential growth. And then from the equation, right, how is this growth pattern shown in the equation? Well, that 2 is telling me something. That 2 is what we call our growth factor. So we'll say that the growth factor is 2, which means that it doubles, that our dependent variable doubles. All right, let's keep going on. The type of relationship, well, is this a linear relationship? No, not at all. So we're just going to say it's not a linear relationship. And then why is it not a linear relationship? Take a few seconds. Tell your neighbor, hey, why is this relationship not linear? Okay, so I would assume that you guys would say something along the lines of, well, it's not linear because the number of ballots doesn't increase by a constant amount. So the number of ballots does not increase by a constant amount. Right, we don't have that constant rate of change here. So therefore, that makes it a nonlinear relationship. Okay? All right. Last part of this lesson here. Suppose Chen could make 20 cuts. How many ballots would he have? How many ballots would he... I think you guys can do these two questions on your own. So pause the video now. Attempt these problems, please. And then play the video again, and I'll walk you guys through it. All right, so hopefully you pause the video. Okay, so C1 says, suppose Chen could make 20 cuts. How many ballots would he have? How many ballots would he have if he could make 40 cuts? Okay, so you need to remember your equation here. T equals 2 to the nth power. And remember that n represents the number of cuts, and t represents the number of ballots. So after 20 cuts, well, does this 20, is it represent n? Does it represent t? Well, we just said that n is the number of cuts, so we are going to plug in 20 in for n. So we're going to say 2 to the 20th power. And what does that equal? Go ahead and type that into your calculator. What you guys will need to do is on the scientific calculators in my classroom, you guys are going to type in 2, then you're going to punch in that little caret sign, right? The caret sign allows you to type in, raise a number to any power you want. Okay, so you're going to punch in the little caret sign, it's on the left side of your calculator, and then you're going to type in your exponent. So your calculator is thinking of this as 2 to the 20th power. Then you're going to press equals, and it's going to give you your answer. And so you should get something like 1,048,576. 1,048,576 ballots. That is a lot of ballots. That is a very large student government association. All right. And then after 40 cuts, something very similar. All we got to do is plug in 2 to the 40th power. Okay? Please do not say, hey, I should just multiply 1,048,576 by 2 because I'm doubling the exponent. No, please no. Type this into your calculator. Right? You're going to do 2, you're going to punch in 2, you're going to do the caret sign, and then you're going to type in 40, then you're going to punch the equal sign, and you're going to get a number like this. There we go. What is that? Hundreds, 100,000s, 100 millions, 100 million. It's a lot. But as you can see, it's definitely not double the amount of 20 cuts. No more linear relationships. We are talking about exponential relationships here. All right, second question. How many cuts would it take to make 500 ballots? Well, I know that 2 to the 20th is over 1 million, so I know that n has to be less than 20. I know that, well, let's actually take a look back at my table here. So it looks like at 9 cuts we're at 510. And the question's asking us how many cuts would it take to make 500 ballots? And I know you guys are probably thinking, well, it's in between 8 and 9, but realistically, can you do like a fraction of a cut? I mean, no, not really. So I guess our best answer that we could say, so to make 500 ballots, it would take at least 9 cuts. 8 cuts is too small. So we have to break the 9 cut point and go beyond that. So, and we said that 2 to the 9th is 510 ballots. So that would meet this criteria. And there you have it. There's the first lesson, lesson 1.1, Introduction to Exponential Growth. All right, I'll see you guys in the next one.